What if everything you thought you knew about the universe was only a fraction of the truth? Picture the cosmos as we see it, vast, mysterious, brimming with galaxies, stars, and planets. But what if the reality is even stranger? Hidden in the fabric of space itself could be dimensions beyond our comprehension, realms folded so tightly we've never detected them. Yet they might hold the keys to understanding everything from gravity to the birth of existence. This isn't science fiction, it's the cutting edge of theoretical physics, where the rules of reality bend and stretch in ways that challenge our deepest assumptions. For centuries, we've believed our universe operates in 3 dimensions of space and 1 of time. But what if that's just the surface? Imagine a world where there are not just 4, but 5, 10, or even more dimensions, curled up so small they're invisible to us, like the tightly wound strings of a cosmic violin. These hidden dimensions aren't just wild speculation, they're serious proposals from some of the brightest minds in science, attempts to solve mysteries that have puzzled physicists for decades. Why is gravity so weak compared to other forces? What truly happened in the first moments of the Big Bang? The answers might lie in realms we can't see, dimensions that shape reality in ways we're only beginning to grasp. Today, we're diving into 30 of the most mind-bending theories about these hidden dimensions, from the elegant twists of string theory to the sprawling landscapes of brain-world scenarios. Each one offers a glimpse into a universe far richer and more bizarre than we ever imagined. Some theories suggest we're living on a membrane floating in a higher dimensional space, while others propose that every particle in existence is actually a tiny, vibrating string dancing through unseen dimensions. The possibilities are as thrilling as they are humbling, because if even one of these ideas is true, it would rewrite the story of the cosmos, so buckle up. By the end of this journey, you'll never look at the universe the same way again. String theory is where the hunt for hidden dimensions begins in earnest, and it starts with a radical idea. What if all the fundamental particles we know, from quarks to electrons, aren't point-like dots at all, but tiny, vibrating strings? These strings would be so small that if you blew one up to the size of a tree, an atom would still dwarf a galaxy by comparison. But here's the twist. For the math behind string theory to work, these strings can't just dance in the 3 spatial dimensions we experience. They need room to vibrate in at least 6 more, possibly even 7. That's where the mind-bending concept of compactification comes in. Think of these extra dimensions like the tightly coiled wires inside an old telephone cord. From a distance, the cord looks like a simple line, one dimension. But up close, you see the spirals hidden within. In the same way, string theory suggests that beyond the sprawling vastness of our 3-dimensional world, 6 or 7 extra dimensions could be curled up into shapes so tiny they're practically invisible. Enter Kaluza-Klein complex, multi-dimensional geometries that might be the hidden scaffolding of reality itself. These shapes, named after the mathematicians who first explored them, aren't just random twists. Their intricate folds determine how strings vibrate, which in turn dictates everything from the mass of particles to the strength of forces like gravity. But why would nature bother with all these extra dimensions? The answer lies in unification. String theory aims to bridge the gap between Einstein's general relativity, which rules the cosmos on large scales, and quantum mechanics, which governs the subatomic realm. In our familiar 4-dimensional space-time, these 2 theories clash violently, but add those extra dimensions and suddenly the equations start to harmonize. It's as if the universe has been playing a symphony all along. We just never noticed the missing instruments. Of course, this raises a tantalizing question. If these dimensions are real, how do we prove they exist? Some physicists speculate that if we could peer into the quantum realm with enough precision, we might spot subtle fingerprints of higher dimensions like gravity leaking into them, which could explain why it's so weak compared to other forces. Others suggest that high-energy particle collisions, like those in the Large Hadron Collider, might reveal exotic particles that only make sense if extra dimensions are at play. For now, these ideas remain just beyond our grasp, but in the quest to uncover the universe's deepest secrets, string theory's hidden dimensions offer one of the most dazzling possibilities yet. Long before string theory danced onto the scene, another bold idea was quietly reshaping how physicists viewed reality. In 1921, mathematician Theodore Kaluza made a stunning proposal: what if the universe had 5 dimensions instead of 4? He took Einstein's equations of general relativity, which described gravity as the bending of spacetime, and stretched them into an extra spatial dimension. The result was electrifying, literally. Kaluza found that this 5th dimension didn't just account for gravity. It also perfectly described Maxwell's equations for electromagnetism, as if the universe had been hiding a secret connection between these forces all along. But how could an extra dimension exist without us noticing? Enter physicist Oscar Klein, who refined the idea a few years later. He suggested this 5th dimension might be curled up into an unimaginably tiny loop, smaller than an atom. So small that even today's most powerful microscopes couldn't glimpse it. Picture a garden hose. From a distance, it looks like a one-dimensional line, but up close, you see it's actually a cylinder. In the same way, Klein argued, every point in our familiar 3-dimensional space could harbor a hidden, circular dimension woven into the fabric of reality itself. For a brief moment, Kaluza-Klein theory promised to unify physics under a single, elegant framework, but cracks soon appeared. When quantum mechanics exploded onto the scene, the theory struggled to explain the behavior of subatomic particles. Worse, no one could figure out why the 5th dimension curled up at such a specific, minuscule size. Without experimental evidence or a way to test its predictions, the idea faded into the background, overshadowed by the quantum revolution. Yet its legacy endured. Kaluza and Klein had cracked open a door that future physicists would walk through, proving that extra dimensions weren't just mathematical quirks, but tools that could reveal deeper truths about the cosmos. Decades later, string theory would resurrect their work in spectacular fashion. Those tightly wound dimensions Kaluza and Klein imagined, they became the blueprint for string theory's extra-spatial dimensions. The idea that hidden geometry could unify forces, it evolved into the ambitious hunt for a theory of everything. Even their stumbling blocks, like the mystery of dimension size, posed questions that still drive research today. What's striking is how prescient their vision was. A century ago, armed with little more than paper and intuition, they glimpsed a multidimensional universe long before modern physics caught up. Their theory may have been shelved, but its spirit lives on, proof that sometimes the boldest ideas are just ahead of their time. What if our entire universe is just one slice of a much larger cosmic loaf? That's the startling premise of Brane cosmology, a theory that reimagines reality as a 3-dimensional brane, short for membrane, drifting within a higher dimensional space called the bulk. Imagine a single page floating in a vast library. We're confined to that page, unaware of the other dimensions just beyond our perception. This idea isn't just poetic, it could solve one of physics' biggest puzzles: why gravity is so inexplicably weak compared to forces like electromagnetism. In the Braneworld scenario, gravity's feebleness might come from its ability to leak into the bulk. Picture a drop of ink on a paper towel. It doesn't just stay on the surface but seeps into deeper layers. Similarly, gravity's influence could be diluted as it spreads into higher dimensions, leaving only a faint shadow in our familiar 3-dimensional world. This would explain why gravity is 10 trillion times weaker than the nuclear forces holding atoms together. The other fundamental forces, though, remain stubbornly bound to our brain, trapped like bugs on a windowpane, which is why we experience them so vividly. The Randall-Sundrum models proposed in the late 1990s gave this wild idea mathematical teeth. One version suggests our universe sits near a warped, higher dimensional boundary, like a ship anchored close to a black hole's gravitational well. The curvature of this space could amplify gravity's effects on our brain while hiding the extra dimensions from view. No need for them to be microscopically small, as in string theory. Another version posits two branes separated by a gap in the bulk, with gravity funneled between them like echoes in a canyon. These models don't just tweak reality, they flip it inside out, offering testable predictions like tiny deviations in gravity at submillimeter scales or exotic high-energy particles that might appear in collider experiments. Brane cosmology also reshapes our cosmic origin story. The Big Bang might have been a collision between two branes, a violent event that seeded our universe with energy and matter. Some theories even suggest these collisions could happen cyclically, meaning our universe isn't the first and won't be the last to emerge from such a cosmic crash. It's a vision that makes the multiverse feel almost pedestrian by comparison, hinting at layers of reality stacked like sheets in a notebook, each with its own laws and histories. While we've yet to find direct proof of branes or the bulk, the theory's elegance keeps it at the forefront of cosmology, a reminder that the universe's greatest secrets might be hiding in plain sight just one dimension away. Most of us picture extra dimensions, if we imagine them at all, as impossibly tiny, curled up smaller than a quark, far beyond any microscope's reach. But what if some hidden dimensions aren't microscopic at all? What if they're large enough, in fact, that you could almost reach out and touch them? This is the radical premise of large extra dimensions, a theory that flips the script on string theory's compactified realms. Instead of vanishingly small loops or Calabi-Yau manifolds, these dimensions could stretch as wide as a millimeter, lurking just beyond the edge of our perception. The motivation behind this idea is as bold as the theory itself, solving the infamous hierarchy problem. In particle physics, there's a baffling mismatch between gravity's weakness and the staggering strength of the other fundamental forces. Electromagnetism, for example, is a trillion times more powerful than gravity, a difference so extreme it's like comparing a candle's flicker to the fury of a supernova. The unsettling question is why. Standard explanations require awkward fine-tuning, as if the universe dialed in an arbitrary number to balance the scales. But large extra dimensions offer a cleaner solution. Gravity isn't weak, it's just diluted. Here's how it works. If gravity can propagate into these extra dimensions while other forces remain trapped in our three-dimensional brane, its influence would spread thinly across a far greater volume of space. Picture a drop of dye in a glass of water. It disperses until it's barely visible. Similarly, gravity's strength in our world might be faint because most of it has leaked into unseen dimensions. This could explain the hierarchy problem without resorting to unnatural numerical coincidences. Suddenly, gravity's feebleness isn't a puzzle. It's a clue pointing to the existence of hidden cosmic real estate. But how large could these dimensions actually be? The lower limit is set by experiments we've already done. Since we haven't detected deviations from Newton's laws at visible scales, say, the width of a hair, the extra dimensions must be smaller than that. But they could still be vast compared to the Planck length, potentially as big as a millimeter. That might not sound impressive, but in particle physics terms, it's gargantuan, enough to reshape our understanding of the quantum world. The hunt for these dimensions isn't just theoretical. Scientists have designed exquisitely sensitive experiments to probe gravity at microscopic distances. Devices like torsion balances and cantilevers measure the gravitational pull between tiny weights separated by gaps as small as a human hair's width. If large extra dimensions exist, gravity should strengthen dramatically at these scales, betraying its hidden pathways. So far, no definitive signal has appeared, but the search continues, refining techniques to explore ever smaller distances where the fabric of space might finally reveal its secrets. What makes this idea so thrilling is its testability. Unlike some cosmic conjectures, large extra dimensions leave fingerprints we can chase. Particle colliders like the Large Hadron Collider could produce Kaluza-Klein gravitons, hypothetical particles that echo through higher dimensions, appearing in our world as missing energy. Or we might spot microscopic black holes, fleeting and tiny, that evaporate in an instant. These phenomena would be smoking guns for dimensions beyond our own. Critics argue that the lack of evidence so far makes the theory unlikely, but its elegance keeps it alive. After all, the universe has surprised us before. Think of dark matter or the cosmic microwave background. The lesson is clear: when the math points somewhere unexpected, it's worth looking. Whether these large dimensions exist or not, their possibility reminds us that reality might be far stranger than it seems. And if we do find them, it would rewrite physics overnight, proving that the cosmos has been hiding its true scale in plain sight. For now, the mystery lingers. But one thing's certain: if dimensions of this size are real, they're not just mathematical curiosities, they're part of the everyday world, closer than we ever imagined. The next time you measure a millimeter on a ruler, consider this. You might be holding a cosmic yardstick marking the edge of known reality. What if the universe we experience, every galaxy, every atom, even our own thoughts, is nothing more than an illusion? A cosmic mirage projected from the edges of reality itself. This is the staggering claim of the holographic principle, a theory that suggests our three-dimensional world might be a hologram encoded on a distant two-dimensional surface. It sounds like science fiction, but the idea emerges from some of the most profound puzzles in physics, starting with a simple question: what happens to information when it falls into a black hole? In the 1970s, physicist Jacob Bekenstein made a startling observation. A black hole's entropy, a measure of its hidden information, doesn't scale with its volume but with its surface area. It was as if everything inside the black hole was somehow written on its event horizon, like data etched onto a celestial hard drive. Stephen Hawking later showed that black holes evaporate over time, radiating energy until they vanish. But this raised a paradox. If the black hole disappears, what happens to all that information it swallowed? Quantum mechanics insists information can't be destroyed, yet general relativity seemed to demand it. The solution, proposed by Leonard Susskind and Gerard T. Hooft, was revolutionary. Maybe the information isn't lost because it was never inside the black hole to begin with. Instead, it's painted onto the boundary, a two-dimensional ledger keeping track of the three-dimensional chaos within. This realization birthed the holographic principle, which posits that our entire universe might operate the same way. Just as a hologram encodes a 3D image on a flat sheet, the cosmos could be a projection from a distant, lower-dimensional surface. The math behind this idea finds its sharpest form in the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT, which shows how a theory of gravity in a higher dimensional space can be perfectly mirrored by a quantum field theory on its boundary, no gravity required. Picture a snow globe. The intricate scenes inside might seem real, but they're just reflections of something simpler painted on the glass. In this framework, the universe isn't just described by physics, it is physics unfolding on a hidden screen we can't see. The philosophical implications are dizzying. If the holographic principle is true, then reality as we know it is a kind of cosmic sleight of hand, a grand illusion where depth and solidity are just artifacts of a deeper, flatter truth. Free will, consciousness, even time itself might be emergent phenomena, shadows cast by a more fundamental layer of information. It's a humbling thought that everything we are, everything we perceive, could be no more substantial than the glow of a movie projector. Yet for all its strangeness, the holographic principle isn't pure speculation. Experiments like the holometer at Fermilab have sought to detect the pixelation of space-time, tiny fluctuations that might betray the universe's underlying digital nature. So far, the results are inconclusive, but the search continues. After all, if there's even a chance we're living in a hologram, it's a mystery worth unraveling, one that could redefine not just physics, but the very nature of existence. What's remarkable is how elegantly this idea ties together some of science's biggest questions. From black holes to quantum gravity, the holographic principle offers a unifying lens, suggesting that the universe's deepest truths might not lie in the fabric of space, but on its edges. It's a reminder that reality, no matter how solid it seems, might be far more malleable and far more mysterious than we ever dared imagine. The Big Bang might not have been the beginning, just the latest chapter in an endless cosmic cycle. This is the bold promise of cyclic universe theories, which propose that our universe undergoes infinite rebirths, each triggered by collisions in a hidden higher dimensional space. Unlike the traditional Big Bang model, where everything explodes from a single point of infinite density, cyclic scenarios imagine our universe as one of many membranes drifting through a vast bulk, destined to collide, rebound, and collide again in an eternal dance. At the heart of this idea is the ekpyrotic theory, derived from the Greek word for conflagration. Picture two colossal branes, flat, three-dimensional sheets floating parallel to each other in a fifth dimension. Normally, they drift apart, but gravity slowly pulls them back together until they smash in a cataclysmic impact. That collision wouldn't just be a cosmic fender bender, it would unleash enough energy to forge an entire new universe. The heat and density would mimic the conditions of the Big Bang, but with a crucial difference. Instead of emerging from a singularity, the newborn universe inherits a subtle imprint of the collision, a cosmic fingerprint left by the geometry of higher dimensions. What's striking is how neatly this solves some of the Big Bang's thorniest puzzles. Take the horizon problem. Why does the universe look so uniform in all directions, as if distant regions were once in contact? In standard cosmology, this requires an awkward fix called inflation, a faster-than-light expansion in the universe's first moments. But in the ekpyrotic model, those far-flung regions were in contact before the collision, stretched and smoothed as the branes drew close. The theory also sidesteps the mystery of what preceded the Big Bang. There's no before in the traditional sense, just an endless series of universes, each born from the ashes of the last. Yet cyclic models aren't without their challenges. Critics point out that brane collisions would likely be chaotic, leaving the universe lumpy and uneven, nothing like the smooth cosmos we observe. Some versions of the theory tweak the physics, suggesting the branes might warp or ripple in ways that preserve uniformity. Others propose that quantum effects in higher dimensions could stabilize the process, like invisible bumpers guiding the branes into a perfectly synchronized crash. The real test, though, is whether these ideas leave detectable traces. If the ekpyrotic scenario is correct, the cosmic microwave background, the afterglow of the Big Bang, might bear faint, telltale patterns left by brane collisions. Some physicists even speculate that gravitational waves from these events could linger, hidden in the fabric of space-time, waiting for future observatories to uncover them. Until then, the cyclic universe remains a tantalizing what-if, a reminder that our cosmic story might not have a single beginning, just an endless loop of endings and rebirths. What's captivating is how this reshapes our place in the cosmos. In the traditional Big Bang, time has a clear starting point, a moment of creation. But in a cyclic world, time stretches infinitely in both directions, with no true origin or finale. Galaxies, stars, even life itself would arise again and again, each iteration subtly different from the last. It's a vision that's as humbling as it is beautiful, one where the universe isn't just expanding but breathing, pulsing with collisions we can't see, in dimensions we've yet to explore. Supersymmetry whispers an elegant secret about the universe, one that could bridge the gap between the particles we know and the hidden dimensions we suspect. At its core, supersymmetry, or SUSY, proposes an audacious symmetry between the two fundamental classes of particles, fermions like quarks and electrons, which make up matter, and bosons like photons, which carry forces. But SUSY isn't just about balancing the cosmic ledger. It's a mathematical key that unlocks the door to higher dimensions in superstring theory, revealing a universe far more interconnected than we ever imagined. To see how, picture the vibrational patterns of strings in superstring theory. These tiny loops don't just wiggle in our familiar 3 dimensions of space, they dance through additional fermionic dimensions, a special kind of mathematical space where the very concept of direction takes on a quantum twist. Unlike ordinary dimensions which describe where something is, fermionic dimensions encode how particles behave, whether they're matter or force carriers, fermion or boson. SUSY stitches these two roles together, suggesting every known particle has a hidden superpartner lurking in these exotic dimensions. An electron might have a selectron, a photon, a photino, and so on. If true, it's as if the universe has been playing a game of cosmic hide and seek with half its particles tucked just out of view. This isn't just theoretical sleight of hand. SUSY extra dimensions could solve some of physics' deepest headaches. Take the infamous hierarchy problem. Why the Higgs boson's mass is so precariously tiny compared to the Planck scale, the natural weight of the universe. Without SUSY, quantum corrections should balloon the Higgs mass to absurdly high values, unless we fine-tune the numbers to an absurd degree. But with supersymmetry, fermionic dimensions provide a cancellation mechanism. Superpartners act as counterweights, delicately balancing the equation so the Higgs stays light. It's like building a house of cards where every card has an invisible twin, steadying the structure against the slightest breeze. Yet for all its elegance, SUSY remains stubbornly elusive. Particle colliders like the Large Hadron Collider have scoured ever higher energies, hunting for signs of superparticles. So far, no selectrons or photinos have appeared in the debris of proton collisions. This doesn't necessarily mean SUSY is wrong, just that superpartners might be heavier than expected, or that they decay in ways we haven't yet detected. Some theorists argue we might need even more powerful colliders to spot them. Others suggest SUSY could manifest in subtler ways, like faint imbalances in particle interactions or unexpected resonances buried in data. The silence of the detectors hasn't dulled the theory's allure, though. SUSY mathematical beauty and its uncanny ability to smooth out string theory's roughest edges keeps it at the forefront of physics. Without supersymmetry, string theory's extra dimensions lack the stability needed to describe our universe. Fermionic dimensions act as cosmic glue, binding together the messy quantum world and the sleek geometry of higher dimensional space. Even if SUSY particles never show up in colliders, their fingerprints might still be etched into the cosmos, hidden in the spin of black holes or the afterglow of the Big Bang. What's thrilling is how SUSY forces us to rethink the nature of reality itself. If fermionic dimensions exist, they're not just more space, they're a shadow realm where matter and force, boson and fermion, are two sides of the same coin. It's a reminder that the universe's deepest symmetries might be invisible to us, woven into dimensions we're only beginning to fathom. For now, supersymmetry remains a tantalizing maybe, a theory so compelling that physicists keep searching, convinced the cosmos has one more card up its sleeve. Think of space not as a flat, rigid grid but as a stretchy fabric bending under the weight of massive objects like stars and planets. Now imagine that same warping effect, but in dimensions we can't see, hidden folds so extreme they could trap gravity itself. This is the mind-bending premise behind warped dimensions, a twist on extra-dimensional theories that turns the cosmos into a cosmic funhouse mirror. Unlike flat extra dimensions where gravity spreads evenly like ink on paper, warped dimensions create gravity hotspots, regions where space is so distorted. It behaves like a steep valley, concentrating gravity's pull in ways that defy our everyday intuition. The Randall-Sundrum models, named after physicists Lisa Randall and Raman Sundrum, bring this idea to life with a vivid analogy. Picture a funnel or a warped throat in higher dimensional space. Our universe sits near the wide end, where gravity is diluted and weak, while the steep slopes of the throat amplify gravity's strength as you descend. It's like comparing the gentle ripples on a pond's surface to the crushing currents at the bottom of a whirlpool. In this scenario, gravity isn't weak because it's leaking into extra dimensions. It's weak because we're stranded in the shallow end of a cosmic pool, far from the deep, intense gravity well hidden in the bulk. What sets warped dimensions apart from flat extra dimensions is their ability to solve two puzzles at once. First, they explain gravity's feebleness without requiring all extra dimensions to be microscopically small. Second, they offer a natural way to localize gravity, keeping it tied to our brain despite the pull of higher dimensional space. Imagine a marble rolling along a warped tablecloth. It might veer toward the dips and curves, but if the fabric is taut enough in certain spots, the marble stays put. Similarly, the warping of space could anchor gravity to our brain, preventing it from dissipating entirely into the bulk. The math behind this is as elegant as it is strange. The Randall-Sundrum models rely on a concept called exponential warping, where the strength of gravity drops off dramatically as you move away from our brain. This isn't just a gentle decline, it's a plunge so sharp that within a fraction of a millimeter in the fifth dimension, gravity's influence becomes negligible. It's why we don't notice these hidden folds in daily life. The warping is so extreme that its effects are confined to scales we've barely begun to probe. But how would we ever detect such a thing? One clue might lie in the behavior of gravitational waves. If space-time is warped in higher dimensions, ripples from distant collisions between black holes could carry subtle distortions, like echoes bouncing off unseen walls. Particle colliders might also reveal hints. High-energy collisions could produce Kaluza-Klein gravitons that decay in distinctive patterns, betraying their journey through warped space. Even the cosmic microwave background, the oldest light in the universe, might bear faint imprints of these hidden contours, etched into the sky like fingerprints on glass. Critics argue that warped dimensions introduce new complexities, like the need for exotic forms of energy to sustain the warping. Yet the theory's explanatory power keeps it alive. It's a reminder that the universe might not play by the rules we're used to, that gravity's gentle tug on Earth could be the faint whisper of something far more potent, coiled in dimensions just beyond our grasp. And if that's true, then every time you drop a pen or feel the weight of your body, you're not just feeling gravity, you're sensing the shadow of a hidden, warped reality. What if gravity isn't the only force sneaking through hidden dimensions? Most theories focus on gravity's peculiar weakness as a clue to extra dimensions, but universal extra dimensions, or UD, turns that idea on its head. In this radical framework, all fundamental forces, from electromagnetism to the strong nuclear force, can propagate through higher dimensional space. Imagine the cosmos as a vast, multi-layered arena where every interaction, light, matter, even the glue holding atoms together, echoes across dimensions we can't see. It's not just gravity leaking into the bulk, it's the entire symphony of physics playing out in realms beyond our perception. This leads to one of UED's most striking predictions, Kaluza-Klein towers. Named after the early pioneers of extra dimensions, these aren't literal structures but a cascade of nearly identical particles, each representing a vibrational mode of their higher dimensional counterparts. Picture a guitar string, pluck it once and you hear a single note, but that string can also vibrate at higher harmonics, producing overtones. In the same way, particles like electrons or photons could have shadows in extra dimensions, each with slightly higher masses corresponding to how they resonate through those hidden spaces. These heavier versions, called Kaluza-Klein partners, would behave almost like the particles we know, but with extra energy stamped by the geometry of unseen dimensions. The implications are staggering. If UED is correct, think the Large Hadron Collider might not just find one new particle but entire families of them, spaced at regular intervals like rungs on a ladder. A single electron collision could produce not just the familiar electron but a heavier KK electron, then an even heavier version, and so on. These particles would decay almost instantly, but their signatures missing energy, unusual momentum distributions, could betray their existence. Some models even suggest that the lightest KK particle might be stable, making it a prime candidate for dark matter, the invisible glue holding galaxies together. But why would nature bother with such complexity? UD offers an elegant answer: universality. Unlike brane-world scenarios where gravity alone ventures into the bulk, UD treats all forces equally, restoring a symmetry that feels more natural to many physicists. It's as if the universe, instead of playing favorites, built its laws to operate seamlessly across every dimension, seen or unseen. This could also solve lingering puzzles in particle physics, like the hierarchy problem, without invoking untested concepts like supersymmetry. Of course, the theory isn't without hurdles. If extra dimensions are large enough to affect all forces, why haven't we spotted their effects already? Proponents argue that the dimensions might still be tiny, just a fraction of a millimeter, but with a twist, they could be compactified in shapes that leave subtle fingerprints only at ultra-high energies. Others suggest that the KK partners might be just beyond the reach of current colliders, waiting for the next generation of experiments to reveal them. The hunt for these signatures is already underway. When protons smash together at nearly the speed of light, detectors scour the wreckage for anomalies, unaccounted energy, unexpected particle tracks, or statistical bumps in the data. So far, no definitive KK towers have appeared, but every new energy level explored brings fresh hope. And if UED is right, the discovery wouldn't just rewrite particle physics textbooks. It would prove that hidden dimensions aren't a niche feature of reality, but the stage on which all physics unfolds, a realm where every force, every particle has a hidden dimension to its story. What if every choice you've ever made spawned another universe, not just metaphorically, but literally, in a hidden dimension just out of reach? This is the spine-tingling promise of mirror universe theories, where parallel realities don't just branch through time but are physically stacked in higher dimensional space. Unlike the quantum multiverse, where every probability plays out in a fractal of alternate timelines, mirror universes could be tangible worlds separated by folds in dimensions we can't perceive, like pages in a cosmic book, each with its own version of you, living a life shaped by slightly different physical laws. The distinction here is critical. In David Deutsch's quantum multiverse, alternate realities emerge from the collapse of quantum wave functions. Every decision, every random event splits the universe into infinite iterations. But mirror universes propose something even stranger, that these alternate realities might coexist in the same quantum state, separated not by probability but by geometry. Think of it like a hallway of mirrors. Your reflection exists in the same moment as you, occupying a space that's nearly identical yet flipped, its light bouncing along a path you can't follow. In higher dimensional physics, these mirror worlds could be literal copies of our universe, displaced along an unseen axis, their particles vibrating in perfect opposition to ours. How would such a thing even arise? One possibility comes from string theory's landscape of vacua, the mind-boggling array of possible universes, each with unique physical constants. If extra dimensions are compactified in certain symmetric shapes, like a Möbius strip or an orbifold, they could produce twin universes with mirrored properties. Electromagnetism might work backward in one. Gravity could repel instead of attract in another. These universes wouldn't just be philosophical abstractions, they'd be physical neighbors, hovering a millimeter away in a fifth dimension, forever cut off from our perception. The implications are dizzying. If mirror matter exists, it could explain some of cosmology's greatest mysteries. dark matter's gravitational pull might be the faint tug of a parallel universe's stars bleeding through higher dimensional space. Or consider the eerie symmetry of antimatter. What if it's not just opposite in charge but a whisper of matter from a mirrored realm? Some theorists even speculate that the Big Bang itself was a collision between two mirror branes, a symmetry-breaking event that spawned twin universes with opposing arrows of time. Yet for all its elegance, the mirror universe hypothesis faces fierce scrutiny. If these realities are so close, why haven't we detected even a glimmer of their existence? The answer might lie in the very nature of higher dimensions. Just as a shadow is a flattened projection of a three-dimensional object, our perception of reality could be a limited slice of something far richer. Forces or particles that traverse extra dimensions might interact so weakly with our brain that their effects are nearly imperceptible, like trying to hear a conversation through a soundproof wall. This is where experiments get creative. Scientists have hunted for mirror matter by studying neutron oscillations, the hypothetical flickering of particles between our universe and its twin. Others probe the cosmic microwave background for anomalous patterns, like temperature asymmetries that could hint at a mirror universe's gravitational nudge. So far, the evidence is scant, but the search continues, driven by a tantalizing possibility that the cosmos isn't just vast but layered, with realities folded into dimensions we're only beginning to imagine. What's haunting is how this reshapes identity itself. In the quantum multiverse, your alternate selves are ghosts of probability, diverging with every choice. But in a mirror universe, another you might be out there, anchored in higher dimensional space, close enough to touch, if only you knew how to reach through the veil. It's a reminder that the universe's greatest secrets might not lie in the distant stars, but in the dimensions hiding in plain sight, waiting for us to tilt our heads and see reality from a new angle. Time doesn't flow, it folds. That's the radical shift in perspective offered by theories treating time not as a fixed arrow but as a higher dimensional structure, woven into the fabric of space in ways we've yet to fully grasp. We're used to thinking of time as the fourth dimension, a steady current carrying us from past to future. But what if time isn't fundamental at all? What if it's an illusion emerging from deeper, more complex dimensions, like shadows cast by a spinning prism? The Wheeler-DeWitt equation, a cornerstone of quantum gravity, hints at this possibility. Developed in the 1960s by physicists John Wheeler and Bryce DeWitt, it attempts to unify general relativity with quantum mechanics by describing the universe's wave function, a mathematical object encoding all possible states of reality. But here's the catch: the equation makes no mention of time. At its core, it paints a picture of a static, frozen universe where change is an illusion, and the past, present, and future exist simultaneously. This timeless view suggests that what we perceive as the flow of time might be a side effect of deeper processes playing out in higher dimensional space. To understand how this could work, imagine a river flowing down a mountain. From a distance, the water seems like a single, unbroken stream times arrow in motion. But zoom in, and you'll see whirlpools, eddies, and currents folding back on themselves. In the same way, higher dimensions could create complex geometries where time's apparent flow is just our limited perspective on a richer, more entangled reality. Some theories even propose that time emerges from the way our three-dimensional, Brane universe moves through a higher dimensional bulk, like a ripple spreading across the surface of a pond. Each moment we experience could be a slice of this deeper motion, a frame in a cosmic film strip we mistake for continuous motion. This challenges everything we assume about cause and effect. If time isn't fundamental, then free will, entropy, even the Big Bang might need rethinking. Take entropy, the measure of disorder that gives time its apparent direction. In a timeless universe, entropy's rise could be an artifact of how we're embedded in higher dimensions, like mistaking the upward slope of a spiral staircase for a straight line. The Big Bang, then, might not be a singular beginning but a geometric feature in a larger, timeless landscape, something we perceive as a starting point only because our senses are locked into lower dimensions. Critics argue that without time, physics loses its predictive power. How can we test a theory that erases the very concept of before and after? Yet supporters counter that time's emergence might be akin to temperature arising from the motion of particles, real in practice but derivative in nature. Experiments could look for subtle violations of quantum mechanics or anomalies in the cosmic microwave background that hint at a deeper, timeless layer. Until then, the idea remains a profound provocation, one that forces us to ask whether time is the stage on which the universe plays, or merely a shadow cast by dimensions we've yet to see. What's thrilling is how this reshapes our place in reality. If time is an illusion, then every moment, every choice, every heartbeat exists eternally in the higher dimensional whole, like notes in a symphony we're hearing one measure at a time. It's a humbling thought that the flow we take for granted might be the universe's most convincing magic trick, hiding its true shape in dimensions beyond our perception. In string theory, the properties of every particle, your electrons, photons, even the elusive Higgs boson, aren't just random quirks of nature. They're locked into place by the hidden geometry of tiny, curled-up dimensions. Picture these compactified dimensions not as bland, uniform loops but as intricate origami folds, each crease and twist shaping how strings vibrate. The way these extra dimensions curve and connect doesn't just add bulk to the universe, it writes the rulebook for physics itself. A string vibrating in a warped, six-dimensional Kaluza-Klein space might become an electron, while one dancing through a differently folded region could emerge as a quark. The mass, charge, and even the very existence of particles hinge on the unseen architecture of these dimensions, like notes in a melody determined by the shape of the instrument. But here's the puzzle. If the universe's extra dimensions can take countless shapes, why settle on the one that gives us the particles and forces we observe? This is the modular stabilization problem, a cosmic, why this and not that. The compact dimensions aren't static. Their sizes and geometries could shift like sand dunes in the wind, altering the laws of physics as they move. Imagine tuning a radio. If the dial slips even slightly, the music dissolves into static. Similarly, if the compact dimensions weren't frozen in just the right configuration, atoms might not hold together, or gravity could overwhelm electromagnetism. String theorists propose that exotic fields or quantum effects lock these dimensions into place, like invisible glue preserving the delicate balance of our universe. Yet the mechanisms remain elusive, a reminder that even the most elegant theories have loose threads. This uncertainty opens the door to the string landscape, a vast, perhaps infinite, collection of possible dimension shapes, each corresponding to a different universe with its own unique physics. Some might be barren, with particles too heavy to form atoms. Others could flicker with bizarre forces we've never witnessed. Our universe, then, might be one page in a cosmic library where the shelving system is written in higher dimensional geometry. Critics argue this makes string theory untestable, a kaleidoscope of possibilities without a clear path to verification. But supporters see it as a strength. The landscape could explain why our universe's constant seems so finely tuned for life, not by design but by sheer statistics, a lucky draw from a deck stacked with every conceivable outcome. The stakes couldn't be higher. If compactified dimensions do dictate particle properties, then finding evidence, say, through subtle discrepancies in particle collisions or gravitational waves, could validate string theory's wildest claims. Conversely, if nature ignores these elegant solutions, it might force a reckoning with our understanding of reality's deepest layers. For now, the shapes of these hidden dimensions remain etched in math, not measurement. But every equation whispers the same tantalizing promise. The universe's blueprints might be hidden in folds too small to see, yet too consequential to ignore. Dark matter might not be some exotic, invisible substance. It could be as ordinary as starlight, just trapped in a reality we can't touch. This is the spine-chilling proposition of Brane world dark matter theories, where the mysterious glue holding galaxies together isn't an unknown particle but familiar matter stranded on a parallel membrane, separated from us by a hair's breadth in higher dimensional space. Imagine two sheets of paper floating a millimeter apart in a pitch-black room. You can't see the other sheet, but its presence warps the air between you, bending light in ways that betray its existence. Now replace those sheets with entire universes, and the warping with gravity suddenly, the unexplainable spins of galaxies start making sense. Here's how it could work. In our universe, stars orbit galactic centers far faster than they should, given the visible matter present. The solution, an invisible halo of dark matter whose gravity provides the extra pull. But instead of invoking hypothetical WIMP or actions, Brane world models suggest this missing mass might be whole galaxies of regular baryonic matter, protons, neutrons, electrons living on a neighboring brane. Gravity, unlike other forces, isn't confined to our membrane. It bleeds into the bulk, the higher dimensional space between branes. So while we can't see or touch that parallel matter, we'd still feel its gravitational shadow, like a neighbor's music vibrating through apartment walls. The math behind this is deceptively elegant. If the bulk is warped, as in the Randall-Sundrum models, gravity's strength could drop off exponentially with distance from our brane. That means matter on a nearby membrane would tug on us just enough to explain galactic rotation curves without requiring undiscovered particles. It's as if the universe handed us two solutions to the dark matter puzzle: invent something new or realize we've been sharing space with invisible twins all along. Critics argue that Brane world dark matter struggles to explain certain observations, like the bullet cluster, where colliding galaxies seem to separate dark matter from visible matter. But proponents counter that higher dimensional gravity could produce similar effects. Imagine two sheets of paper crumpling in a breeze, their gravitational imprints shifting unpredictably. Others point to action-like particles as simpler solutions, yet the Brane world approach holds a unique allure. It doesn't just solve a mystery, it redefines our cosmic neighborhood, suggesting that what we call dark might simply be matter living next door, so close yet forever out of reach. The real test: gravity wave astronomy. If dark matter is ordinary stuff on another brane, colliding black holes might produce faint gravitational echoes, ripples distorted by unseen dimensions. Or future quantum sensors could detect the subtle tremble of a parallel galaxy passing through ours, its mass warping spacetime like a ship's wake in an invisible sea. Until then, the idea lingers, a tantalizing whisper that the universe's greatest secret might not be hidden in the dark, but just around an unseen dimensional corner. Quantum entanglement has long been physics' most beguiling magic trick: particles linked across vast distances, instantaneously mirroring each other's states no matter how far apart they fly. Einstein called it spooky action at a distance, a phrase that captures both its mystery and his discomfort. But what if this spookiness isn't about action at all? What if entangled particles aren't communicating but are secretly connected through hidden corridors in higher dimensional space? This is the radical vision of the ER=EPR conjecture, a theory that stitches together two of Einstein's most famous ideas, wormholes and entanglement. In 1935, Einstein and Nathan Rosen proposed that black holes might be bridged by tunnels through space-time, Einstein-Rosen bridges or wormholes. That same year, Einstein teamed with Boris Podolsky and Rosen to describe entanglement EPR paradox, arguing that quantum mechanics must be incomplete because it allowed for this eerie, instantaneous connection. For decades, these ideas seemed unrelated, one a quirk of quantum theory, the other a speculative feature of general relativity. But in 2013, physicists Juan Maldacena and Leonard Susskind suggested they're two sides of the same coin. Every pair of entangled particles might be joined by a microscopic wormhole, a hidden thread woven through extra dimensions. Think of it like this: two people standing on opposite sides of a mountain could take hours to meet by hiking around it, or they could shake hands instantly if a tunnel bored straight through. In our three-dimensional world, the mountain seems impassable, but at a higher dimension, and the shortcut appears. Similarly, entangled particles might seem impossibly linked across light years when viewed from our limited spatial perspective. But if their connection snakes through a warped fifth dimension, their instantaneous correlation makes geometric sense. The wormhole doesn't transmit information faster than light. It simply redefines distance, turning a marathon into a handshake. The implications are staggering. If ER equals EPR holds, then quantum entanglement isn't just a feature of the subatomic world, it's evidence of spacetime's hidden architecture. Every entangled pair, from lab-manipulated electrons to particles born in the Big Bang, could be tied by microscopic bridges in higher dimensional space. This would blur the line between quantum mechanics and gravity, suggesting that the fabric of spacetime itself emerges from a web of entangled connections. It's as if the universe runs on quantum threads, stitching reality together from behind the scenes. Skeptics point out that these wormholes would be fantastically unstable, collapsing before any meaningful traversal could occur. But supporters counter that stability might not matter. The wormholes could be purely geometric, not traversable in any practical sense, yet still encoding entanglement's math. Others argue that if extra dimensions exist, they could provide the scaffolding needed to sustain these structures, however briefly. Experiments remain a challenge. Wormholes are notoriously camera-shy, and no current technology can probe spacetime at the scales where these microscopic bridges might exist. Yet indirect tests could look for signatures in quantum systems, like anomalies in entanglement entropy or unexpected correlations in particle collisions. Some theorists even suggest that advanced quantum computers might one day simulate wormhole dynamics, offering a digital window into higher dimensional physics. What's profound is how this reshapes our view of reality. If entanglement is gravity's twin in disguise, then the universe isn't just stranger than we imagine. It's stranger than we can imagine, with every quantum connection a whisper from dimensions we can't see. The next time you hear about particles communicating across cosmic distances, remember, they might not be talking at all. They could simply be holding hands through a hidden door we've yet to find. Cosmic strings sound like something ripped from the pages of science fiction, threads of pure energy thinner than an atom yet stretching across the universe, with the mass of entire galaxies packed into every inch. But these bizarre objects might not just be hypothetical. They could be scars left over from the violent birth of higher dimensions, topological defects where the fabric of spacetime itself knotted and froze during the universe's earliest moments. Unlike the cosmic strings predicted by conventional physics, which form during phase transitions in our familiar four-dimensional spacetime, these superstrings could be relics of extra dimensions snapping into place, a cosmic fingerprint of the hidden geometry that shapes reality. Here's how it could happen. Imagine the early universe cooling from an unfathomable heat, like metal hardening as it leaves a forge. As temperatures dropped, the symmetries governing the cosmos broke, locking in the laws of physics we know today. But if extra dimensions exist, their compactification wouldn't have been smooth. Some regions might have twisted or folded faster than others, creating defects, kinks in spacetime that couldn't smooth themselves out. These defects would manifest as cosmic superstrings, infinitely long filaments of trapped energy humming with the echoes of higher dimensional vibrations. Think of it like freezing a glass of water. The ice forms in jagged patterns because the molecules can't align perfectly all at once. In the same way, cosmic superstrings could be the cracks left behind as extra dimensions crystallized into their current form. What sets these superstrings apart from their conventional cousins, traditional cosmic strings predicted by grand unified theories, are one-dimensional scars from phase transitions in our four-dimensional spacetime. They're like cracks in ice formed when the universe's symmetry broke as it cooled. Superstrings, though, are fundamentally different. Born from the breakdown of higher dimensional symmetries, they'd carry unique signatures, extra vibrational modes, peculiar gravitational lensing effects, or even the ability to thread through branes in ways ordinary strings couldn't. Some models suggest they'd be far more stable, persisting for billions of years without fraying or evaporating. Others propose they might interact with dark matter or even act as seeds for galaxy formation, their immense gravitational pull sculpting the cosmos in ways we're only beginning to understand. The hunt for these cosmic threads is already underway. Astronomers scour the sky for telltale distortions in starlight, double images of distant quasars, or strange, linear gaps in the cosmic microwave background. Gravitational wave detectors listen for the faint tremors of superstrings snapping or colliding, events that would send ripples through spacetime itself. And while no definitive evidence has surfaced yet, the search is far from over. If superstrings exist, they'd be more than just cosmic curiosities. They'd be proof that the universe's hidden dimensions aren't just mathematical abstractions, but dynamic, physical entities that left their mark on reality. What's mesmerizing is the scale of these objects. A single cosmic superstring, thinner than a proton, could loop from here to the edge of the observable universe. Pluck one like a guitar string, and it might vibrate for eons, ringing with the harmonics of dimensions we can't see. They're reminders that the universe's grandest structures might be woven from the smallest, most hidden threads, and that somewhere out there, beyond the limits of our perception, the ghosts of extra dimensions could still be pulling the strings. At energies beyond our wildest experiments, where particles collide with the fury of the universe's birth, something bizarre might happen to the very fabric of space. Dimensions, those fundamental stages where reality plays out, could begin to vanish, not in the sense of dissolving into nothing, but by becoming so tightly wound, so scrambled by the chaos of quantum gravity, that they effectively cease to function as dimensions at all. Picture a snowflake melting in reverse. As temperatures rise, its intricate structure collapses into a featureless drop. Similarly, at the Planck scale, the realm where gravity and quantum mechanics clash, spacetime itself might simplify, shedding dimensions until only two remain. This isn't just wild speculation. It's a radical solution to one of physics' deepest paradoxes, where the rules of the cosmos rewrite themselves in the crucible of extreme energy. The math behind this idea is as unsettling as it is elegant. In string theory, where extra dimensions are curled up into microscopic shapes, those same dimensions could freeze or deactivate when energies reach critical levels. Imagine a guitar string tuned so tightly it snaps, no more vibrations, no more music. At Planck energies around 10 to the 19th gigaelectronvolts, the vibrations of strings might become so frenzied that the extra dimensions they depend on lose their meaning, leaving only the barest skeleton of spacetime, a flat, two-dimensional plane where gravity and quantum forces finally speak the same language. Some theories even suggest this dimensional reduction isn't just a quirk of string theory, but a universal feature of quantum gravity, a cosmic failsafe preventing physics from tearing itself apart at the seams. What would this mean for our understanding of reality? For starters, it could explain why gravity seems so weak in our everyday world. If extra dimensions switch off at lower energies, gravity's strength would be diluted, spread thin across dimensions that no longer fully exist from our perspective. It's like trying to fill a swimming pool with a hose that keeps kinking the waters there, but it can't flow freely. This might also resolve the infamous singularity problem at the heart of black holes. Instead of infinite density, a black hole's core could be a two-dimensional surface where physics becomes mathematically tidy. a place where the chaotic dance of quantum gravity finally finds its rhythm. Critics argue that vanishing dimensions sound more like mathematical sleight of hand than testable physics. After all, how do you probe energies a quadrillion times higher than the Large Hadron Collider's limits? Yet supporters point to indirect clues. If dimensions disappear at high energies, they might leave faint imprints on the cosmic microwave background, anisotropies that look like scars from the universe's early, dimensionally chaotic youth. Others suggest that the way particles scatter in high-energy collisions could reveal subtle deviations, hints that spacetime's texture changes when pushed to its limits. The most tantalizing implication is philosophical. If dimensions can vanish, then the stage of reality isn't fixed, it's fluid, adapting to the energy of the moment. The cosmos we know, with its 4 familiar dimensions, might just be the calm after a storm, a low-energy illusion hiding a far stranger, more mutable truth. And if that's the case, then the deepest laws of physics aren't written in stone, they're written in energy, erasable and rewritable as the universe itself evolves. What if spacetime isn't smooth like glass, but jagged and fragmented like shattered crystal at the smallest scales? This is the startling vision of quantum foam, a seething, fractal landscape where dimensions themselves lose their whole numbered certainty. Down in this subatomic chaos, space might not have 3 crisp dimensions, nor time a single unbroken flow. Instead, reality could dissolve into fractions, 2.7 dimensions here, 3.3 there, as if the universe can't quite decide how to structure itself when no one's looking. Loop quantum gravity paints this picture with startling precision. Imagine spacetime not as a continuous fabric, but as a vast weave of tiny, indivisible atoms of space, each 100 billion times smaller than an atom's nucleus. These quantized chunks don't connect neatly like Lego bricks. They tangle into a dynamic web called a spin network, where every intersection vibrates with quantum information. The mind-bending twist, the dimensionality of this network fluctuates wildly depending on how you measure it. Zoom out far enough and it averages to the 3 dimensions we know. But probe closer and the fractal geometry emerges like staring at a coastline that grows more intricate the nearer you get. This isn't just mathematical whimsy. The fractional dimensions of quantum foam could solve long-standing paradoxes. Take black holes. Their singularities grind physics to a halt because all known laws assume smooth, whole-numbered dimensions. But if spacetime is inherently fractured at the Planck scale, singularities might simply be regions where dimensionality crumples to near zero, preventing infinite densities. Even vacuum energy, the mysterious force accelerating the universe's expansion, could arise from this frothy texture as fluctuations in dimensionality create tiny pockets of repulsive gravity. The implications ripple outward. If spacetime has fractal dimensions at its core, then particles might tunnel through extra-dimensional folds we can't perceive, explaining quantum entanglement's spooky connections. Dark energy could be the thermodynamic cost of maintaining dimensionality across cosmic scales. Even the Big Bang might not have been a singularity, but a phase transition where fractional dimensions crystallized into the orderly space we recognize today. Experimental probes are still in their infancy, but ingenious methods are emerging. Some physicists analyze gamma-ray bursts for signs of fractal spacetime slowing high-energy photons. Others hunt for telltale noise in gravitational wave detectors, statistical whispers of dimensionality flickering at the smallest scales. The challenge is that quantum foam's structure would manifest only at energies a trillion times beyond our current colliders. Yet the math insists, if loop quantum gravity is right, then beneath the serene surface of reality lies a churning ocean of fractional dimensions, forever reshaping the stage on which existence plays out. The vacuum of space isn't empty, it crackles with energy, a seething quantum foam that should, by all accounts, rip the universe apart. This is the cosmological constant problem, one of physics' most glaring contradictions. Why does the observed vacuum energy driving the universe's expansion measure a staggering 120 orders of magnitude weaker than what quantum field theory predicts? The math says space-time should be a turbulent storm of repulsive gravity, yet we find it eerily calm, like a breeze barely strong enough to flutter a leaf. Hidden dimensions might hold the answer not by brute force, but through a cosmic sleight of hand, a relaxation mechanism where higher dimensional geometry gently bleeds off excess energy, tuning the universe to improbable perfection. Brane cosmology offers a dazzling twist on this tuning. Picture our universe as a membrane floating in a higher dimensional bulk, like a sheet of paper suspended in a dark room. The vacuum energy on our brain isn't isolated, it interacts with the bulk's curvature, warping the fabric around it. Some models suggest this warping acts like a pressure valve. As vacuum energy builds, the brain flexes into the bulk, dissipating energy into extra dimensions where its gravitational impact fades. It's as if the universe has built-in shock absorbers, quietly siphoning off the violent quantum fluctuations that should tear reality apart. The numbers work out eerily well. Certain brain configurations can naturally suppress the cosmological constant to the tiny value we observe, no fine-tuning required. But how does this relaxation actually happen? One proposal involves a dynamic balancing act between brains. Imagine two membranes separated by a fifth dimension, each with its own vacuum energy. As they oscillate or drift closer, their gravitational pull can cancel out portions of each other's energy, like two waves colliding to create a momentary calm. Another idea, inspired by string theory's landscape of vacua, posits that higher dimensional space offers countless stable configurations, some with negligible cosmological constants, and quantum fluctuations nudge universes toward these life-friendly states over eons. The implications are profound. If extra dimensions regulate vacuum energy, they're not just mathematical curiosities, they're cosmic peacekeepers, maintaining the delicate balance that allows galaxies, stars, and life to exist. Critics argue these models often rely on unproven assumptions about bulk physics or brain dynamics, but supporters counter with a simple truth. Without such mechanisms, the universe's improbable stability becomes inexplicable. The hunt for evidence continues in unexpected places. Subtle anomalies in gravitational lensing, deviations in the cosmic microwave background, or even signatures in high-energy particle collisions that hint at energy leaking into higher dimensions. What's striking is how elegantly this solves a problem that once seemed intractable. The cosmological constant isn't just a number, it's a clue pointing toward dimensions we can't see, but whose influence shapes the universe at every scale. Whether through brain relaxation, dimensional cancellation, or some deeper mechanism still undiscovered, the message is clear. The cosmos might owe its existence to hidden layers of reality, quietly stabilizing the stage on which our story unfolds. The early universe wasn't just hotter and denser. It might have been simpler, a place where the very concept of dimensionality was still in flux. Imagine the cosmos moments after the Big Bang as a seething cauldron of energy, so chaotic that space itself hadn't yet settled into the three dimensions we know today. According to the Brandenburger-Waffe mechanism, this primordial frenzy could have temporarily frozen out extra dimensions, leaving only a handful, perhaps just one or two, to dominate the physics of the newborn universe. It's as if the fabric of reality was still being woven, with threads of space and time tangling and untangling until a pattern we recognize finally snapped into place. How could dimensions simply vanish? The answer lies in string theory's peculiar behavior at extreme energies. In the earliest instance, strings, the fundamental loops of energy that make up particles, would have been so energetic that their vibrations couldn't stabilize in extra dimensions. Picture a guitar string stretched too tight. It can only vibrate in the simplest, most stable modes. Similarly, the universe's strings might have oscillated overwhelmingly along a few preferred directions, rendering the other dimensions temporarily inert. Only as the cosmos cooled and expanded during inflation would these extra dimensions thaw, uncurling from their compacted state and integrating into the geometry we observe now. Thermal string gas cosmology takes this idea further, proposing that the early universe resembled a dense, hot gas of strings colliding and entangling. In this soup, the number of observable dimensions wasn't fixed but depended on the system's equilibrium. Some calculations suggest that 3 spatial dimensions naturally emerge as the most stable configuration, too few, and strings can't avoid intersecting, leading to a messy, unstable universe, too many, and their vibrations dilute too thinly to form coherent structures. It's a cosmic Goldilocks scenario. 3 dimensions isn't just an accident, but the only arrangement where complexity and eventually life could arise. The implications are staggering. If this model holds, the reason we experience 3 dimensions of space isn't just happenstance. It's the universe solving an optimization problem, fine-tuning its own geometry to allow galaxies, stars, and planets to exist. Critics argue that the mechanism remains speculative, lacking direct experimental proof. Yet supporters point to subtle clues that might linger in the cosmic microwave background, anisotropies or polarization patterns that betray the universe's dimensional growing pain. Others suggest that gravitational waves from the inflationary era could carry echoes of this transition, like seismic waves from a distant earthquake. What's haunting is how this reshapes our origin story. The Big Bang wasn't just an explosion of matter and energy. It might have been a dimensional metamorphosis, a moment when the universe chose its shape from an infinite menu of possibilities. And if that's true, then the 3 dimensions we call home aren't just the stage of reality. They're the survivors of a cosmic sieve, the only configuration where the show could go on. What if consciousness isn't confined to the 3-dimensional world we perceive? Some of the most provocative theories in physics and neuroscience suggest that our minds might be tapping into hidden dimensions. Experiences that feel transcendent or otherworldly could actually be glimpses of realities beyond our usual sensory limits. Think about moments when perception seems to expand during deep meditation, near-death experiences, or psychedelic journeys. People describe sensations of infinite connection, distorted time, or even encounters with entities that defy ordinary geometry. These aren't just hallucinations, they might be the brain's imperfect translation of higher dimensional information, like a 2-dimensional creature suddenly perceiving depth for the first time. The idea gains traction when you consider how the brain processes reality. Our perception is already a filtered reconstruction, a flat projection of a richer world. Color, sound, and touch are just interpretations of electromagnetic waves and vibrations. So why couldn't consciousness, under certain conditions, access data from dimensions we can't normally perceive? Mathematician Bernardo Kastrup proposes that psychedelics might temporarily disrupt the brain's reducing valve, a mechanism that narrows our awareness to survival-relevant input. Without this filter, the mind could be flooded with raw, multidimensional input, explaining why users report seeing fractal geometries or feeling merged with infinite spaces. These experiences eerily resemble the complex topologies of Kaluza-Klein manifolds in string theory, as if the brain is glimpsing the hidden scaffolds of reality. Even more striking are accounts from those who have undergone ketamine therapy or DMT experiences, often describing encounters with higher dimensional beings. While skeptics dismiss these as neural noise, some theorists like neuroscientist Andrew Gallimore argue that the brain's default mode network responsible for our sense of self and linear time might act as a dimensional anchor. When this network quiets, consciousness could escape its usual constraints, like a character in a video game realizing they're part of a larger program. The beings described often exhibit impossible movements or morphing shapes, behaviors that align with how a four-dimensional entity might appear to our three-dimensional perception, always partially obscured, like a shadow cast by a rotating hypercube. Ancient mystics might have been onto something too. Sacred texts from the Vedas to Kabbalah describe layered realities or planes of existence that sound suspiciously like higher dimensions. The Tibetan Book of the Dead speaks of bardos, intermediate states where time dissolves and space becomes malleable. Could these traditions be encoding encounters with dimensions science is only now beginning to model? Physicist Claude Swanson notes that near-death experiencers often report floating outside their bodies with 360-degree vision, a perspective that mirrors how a four-dimensional observer would perceive our 3D world, able to see all sides of objects simultaneously, unconstrained by a single vantage point. The implications are staggering. If consciousness can interact with extra dimensions, it challenges the materialist view that the mind is purely a byproduct of the brain. Instead, the brain might be more like a receiver, tuning into a broader, multidimensional reality. Experiments with psychedelics in controlled settings show measurable changes in brain entropy, a sign of heightened information processing that could correlate with accessing more complex dimensional data. Meanwhile, quantum theories like orchestrated objective reduction, ORCH, or proposed by Roger Penrose and Stuart Hameroff, suggest that consciousness arises from quantum vibrations in microtubules, structures that might resonate across higher dimensional spacetime. Of course, critics argue these ideas stretch science beyond its limits. Without empirical proof, they remain speculative, beautiful metaphors rather than testable hypotheses. Yet the overlap between mystical experiences, psychedelic phenomenology, and cutting-edge physics is hard to ignore. Whether these phenomena are truly dimensional or simply the brain's poetic way of interpreting its own complexity, they push us to ask, is reality more layered, more strange than our everyday senses suggest? The answer might lie not in the stars, but in the unexplored dimensions of the mind itself. Gravity doesn't always behave the way Newton or Einstein predicted. On cosmic scales, stars orbiting galaxies move too fast. Galaxies in clusters whip around too quickly, phenomena we usually chalk up to dark matter's invisible pull. But what if the answer isn't an unseen substance at all? What if gravity itself is different in ways we can't perceive because its true nature is hidden in dimensions beyond our own? This is the daring proposition at the heart of modified gravity theories like modified Newtonian dynamics, where the rules of gravity change subtly under certain conditions. And when you peel back the math, something astonishing emerges. These tweaks to gravity might not be arbitrary patches, but shadows of a deeper, higher dimensional reality. Mund's premise is simple yet radical. Instead of invoking dark matter to explain galactic rotation curves, it proposes that gravity weakens less rapidly at extreme distances than Newton's inverse square law predicts. Picture a magnet's pull fading slowly when you're close but dropping off sharply once you're far away, except here, the magnet is gravity itself. The results are striking. For many galaxies, Mund-adjusted equations match observed star speeds without dark matter, as if gravity has a secret second wind at cosmic scales. Critics argue Mund struggles with larger structures like galaxy clusters, but its persistence hints that we might be missing a piece of the puzzle, that missing piece. Extra dimensions could be bending gravity's behavior in ways that look like modified laws from our limited perspective. Here's how it could work. In higher dimensional theories like brain-world scenarios, gravity isn't confined to our three-dimensional membrane, it spills into the bulk, the hidden space between brains. This leakage could warp gravity's apparent strength, making it seem weaker or stronger depending on scale. Imagine water draining from a bathtub. From above, the flow seems smooth, but if you could see the pipes beneath, you'd notice twists and folds altering the water's path. Similarly, extra dimensions might distort gravity's flow, creating effects we misinterpret as dark matter or as evidence for MUND. In some models, this distortion mirrors MUND predictions almost exactly, as if the theory is accidentally brushing against a deeper truth about spacetime's hidden geometry. The contrast with dark matter is stark. Dark matter assumes an invisible particle permeating space, while modified gravity suggests our understanding of force itself is incomplete. But higher dimensional physics offers a third path, a bridge between the two. For instance, certain brain world setups produce gravitational effects indistinguishable from dark matter's pull, no exotic particles required. Other theories propose that what we call MUND, modified gravity, is just ordinary gravity viewed through the lens of compactified dimensions, like hearing music through a wall and mistaking the muffled notes for a new melody. The debate is far from settled. Dark matter has clinched victories, like the bullet cluster's stark separation of visible matter from gravitational lensing. Yet MONDians counter that emergent gravity from hidden dimensions could replicate such phenomena. The real test may come from future experiments probing gravity at microscopic scales where extra dimensions, if they exist, should leave fingerprints. If we find deviations from Newton's laws at certain distances, it wouldn't just validate MUND, it might fling open a door to dimensions we've never seen. What's fascinating is how this reframes the quest for cosmic truth. For decades, dark matter and modified gravity have been framed as rivals, but hidden dimensions suggest they might be two faces of the same mystery. Whether gravity's quirks come from unseen particles or unseen dimensions, the lesson is the same. The universe is far stranger than it appears, and as we dig deeper, we might find that the laws we thought were broken were simply written in a language we're only beginning to understand, one where every equation has hidden variables and every force whispers secrets from beyond the dimensional veil. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate vaults, locking away anything that crosses their event horizon, or so we thought. One of physics' most baffling puzzles is the black hole information paradox. If information can't be destroyed, how does it survive being swallowed by a black hole? The answer might lie not in the depths of the singularity, but in the hidden folds of extra dimensions, where the rules of space and time rewrite themselves in ways that could preserve information against all odds. Enter the AD/CFT correspondence, a groundbreaking idea that ties together gravity in higher dimensional space with quantum theories on its boundary. Picture a black hole in a five-dimensional anti-de Sitter space, a curved, saddle-shaped universe where gravity behaves radically differently. According to AD/CFT, everything that happens inside this black hole is perfectly mirrored by a quantum system living on its four-dimensional boundary, like a hologram encoding 3D data on a 2D surface. In this framework, information isn't lost, it's transformed, translated into a language that doesn't rely on the destruction of spacetime. The event horizon becomes a cosmic Rosetta Stone, preserving data in higher dimensional geometries we're only beginning to decode. This isn't just abstract math, it could resolve the infamous firewall paradox. Imagine falling toward a black hole's event horizon. Quantum mechanics says you should experience nothing unusual, while general relativity predicts you'd be incinerated by a wall of energy. But if extra dimensions are in play, the contradiction melts away. Information might escape the black hole not by burning up at the horizon, but by leaking into higher dimensional space like water seeping through microscopic cracks in a dam. The firewall could be an illusion, a mirage created by our limited three-dimensional perspective, while the real drama unfolds in dimensions we can't see. The implications are staggering. If black holes preserve information through higher dimensional channels, it would mean the universe has a built-in backup system, a fail-safe against cosmic annihilation. This could even reshape our understanding of entropy, suggesting that what we call disorder might just be information we're not equipped to perceive. Picture a scrambled hard drive. To us, the data seems lost, but to someone who understands the underlying code, every bit is still intact. Similarly, black holes might not be the end of information, just the beginning of its journey into dimensions beyond our reach. Critics argue that ADS/CFT's idealized models don't perfectly match our real, expanding universe. Yet the principle holds a tantalizing promise that the key to physics' greatest paradoxes might not lie in pushing deeper into the unknown, but in stepping sideways into dimensions we've yet to explore. Whether through holographic boundaries or hidden geometric escapes, one thing's certain: black holes aren't the dead ends we once thought. They could be gateways, their secrets written in the fine print of spacetime's hidden layers. Time's relentless march forward, the reason shattered glass never reassembles, why we remember the past but not the future, might not be a fundamental law of nature but an accident of geometry. The arrow of time, that stubborn asymmetry driving the universe toward disorder, could be a ghost of higher dimensions, a shadow cast by the hidden folds of spacetime itself. At first glance, thermodynamics seems straightforward. Entropy always increases, carving a one-way path through reality. But dig deeper and the mystery thickens. Why did the universe start in such an improbably low entropy state? The answer might lie not in the laws we know, but in dimensions we've yet to see. Picture a deck of cards shuffled into perfect order by pure chance. Statistically, it's possible, but so unlikely you'd suspect a trick. The early universe presents the same puzzle. How did it land in such a pristine, low-entropy configuration? One radical solution comes from the holographic principle, where our three-dimensional reality projects from a two-dimensional boundary. In this framework, entropy isn't just a property of matter, it's tied to the geometry of the underlying surface. A higher dimensional universe might have started with naturally low entropy simply because its boundary geometry was smooth and simple, like a blank canvas before the brushstrokes of time added complexity. But entropy isn't the only enigma. Boltzmann brains the unsettling idea that self-aware entities could randomly fluctuate into existence from chaos, become even stranger in a multidimensional cosmos. In our familiar three-dimensional world, a Boltzmann brane materializing from random particle collisions is absurdly improbable, but add extra dimensions and the math shifts. If higher dimensional space contains regions where entropy fluctuates wildly, isolated pockets of consciousness could emerge far more easily, like bubbles forming in a boiling pot. Some theories even suggest that these branes might not be isolated minds, but fragments of a larger, entangled reality, their perception of time's arrow shaped by the dimensional folds around them. The real twist: extra dimensions could explain why we don't see Boltzmann branes everywhere. If our universe is a membrane floating in a higher dimensional bulk, the conditions for spontaneous consciousness might only arise in specific, warped regions, places where the geometry of space temporarily mimics the order we associate with the past. We don't encounter these phantom observers because they're trapped in dimensional backwaters, like reflections in a house of mirrors we can't enter. Critics argue this veers into metaphysical speculation, but the math holds surprising weight. String theory's landscape of vacua, those countless possible universe configurations, includes scenarios where the arrow of time isn't fixed but depends on how dimensions compactify. In some, time might even loop or branch, creating universes where cause and effect run backward from our perspective. The takeaway isn't just that time's arrow is flexible, but that its direction might be a local phenomenon, as arbitrary as the north-south divide on a compass. What's humbling is how this reframes our place in the cosmos. The steady flow of time, the certainty that yesterday precedes today, might not be universal truths, just quirks of the dimensional neighborhood we inhabit. If higher dimensional geometry dictates entropy, then the arrow of time isn't a law written in stone, but a trail marked in the sand, shaped by winds we're only beginning to sense. And if that's true, then every moment, every irreversible step forward, might be a fleeting echo of dimensions we can't see, but whose influence is written into the fabric of every passing second. If hidden dimensions exist, coiled up tighter than the span of an atom, how could we ever hope to detect them? The answer might lie not in seeing these dimensions directly, but in tuning our instruments to the faint vibrations echoing through the fabric of reality itself. Just as plucking a guitar string produces distinct musical notes, the compactified dimensions of string theory could resonate at specific frequencies, sending ripples through our observable universe. These aren't just hypothetical whispers, they could leave tangible fingerprints in particle colliders, gravitational wave detectors, and even the afterglow of the Big Bang. At the heart of this idea are Kaluza-Klein gravitons, hypothetical particles named after the pioneers of extra dimensions. In theories with compactified dimensions, a graviton, the quantum particle of gravity, wouldn't just move through our familiar 3 dimensions of space. It would also oscillate through the extra curled-up dimensions, like a marble rolling along the grooves of a microscopic labyrinth. These extra motions aren't free, they're quantized, meaning the graviton can only vibrate at certain discrete energies. Each allowed vibration corresponds to a heavier copy of the graviton, a Kaluza-Klein tower of particles, each with a mass proportional to how tightly the extra dimensions are wound. The implications are staggering. If these KK gravitons exist, they'd behave like ghosts in the machine of particle physics, invisible to detectors but stealing energy from collisions. Imagine smashing protons together at nearly the speed of light. If a KK graviton pops into existence, it would vanish into the bulk of higher dimensional space, leaving behind an eerie signature, missing energy, a gap in the expected momentum of the collision debris. The Large Hadron Collider has scoured its data for precisely these anomalies, hunting for imbalances that can't be explained by ordinary particles. While no definitive signal has emerged, the search continues at higher energies where heavier KK modes might finally reveal themselves. But colliders aren't the only way to listen for dimensional echoes. The cosmic microwave background, the oldest light in the universe, might hold subtler clues. If extra dimensions vibrated intensely during the universe's infancy, they could have imprinted faint patterns in this primordial radiation, like grooves on a vinyl record. Some models predict spiral-shaped polarization patterns or anomalous temperature fluctuations that defy standard cosmology. Others suggest that gravitational waves from the early universe, if ever detected with enough precision, could carry harmonics from compact dimensions, like a bell's overtones betraying its hidden cracks. The wildest possibility, these resonances might not even require extra dimensions at all. Certain quantum gravity models propose that space-time itself could have a granular, foamy structure at the tiniest scales, producing vibration-like effects that mimic KK gravitons. It's a sobering reminder that nature often disguises her secrets. What looks like a higher dimensional signal might be something even stranger. For now, the hunt remains one of physics' most exhilarating gambles. Finding KK gravitons wouldn't just confirm hidden dimensions, it would rewrite our understanding of gravity, quantum mechanics, and the birth of the cosmos. And if the search comes up empty, that silence might speak volumes, forcing us to rethink whether dimensions are curled up too tightly to detect, or whether reality's blueprint is stranger than we ever imagined. Either way, the universe is playing a tune. We're just learning how to listen. Einstein's general relativity paints gravity as the graceful bending of space-time, a cosmic dance where planets and stars move along curves in a 4-dimensional fabric. Meanwhile, quantum mechanics describes a frantic, probabilistic world where particles flicker in and out of existence, governed by uncertainty. These two theories work flawlessly in their own domains, but when they collide, like at the center of a black hole or the Big Bang's infancy, physics breaks down into mathematical chaos. Hidden dimensions might be the missing mediators in this century-old feud, offering a backstage pass to a unified theory where gravity and quantum forces finally harmonize. String theory takes the most celebrated swing at this unification, proposing that the quantum jitters of particles are actually the vibrations of tiny strings wriggling through 10 or 11 dimensions. In this framework, gravity's gentleness compared to other forces isn't a bug, it's a feature. The graviton, the hypothetical particle carrying gravity, could be a closed-loop string vibrating across extra dimensions, its influence diluted as it leaks into the bulk of higher dimensional space. Meanwhile, the other forces remain confined to our three-dimensional brain, burning bright and strong. It's an elegant solution, but one with glaring gaps. Where's the experimental proof? Why do Kaluza-Klein manifolds, the intricate shapes of extra dimensions, take one form over another? Loop quantum gravity, LQG, takes a starkly different approach. Instead of adding dimensions, it reimagines space-time itself as a web of interconnected atoms of space, a granular structure where geometry emerges from quantum interactions. Here, extra dimensions aren't prerequisites but potential byproducts like bubbles forming in boiling water. LQG's spacetime isn't smooth and continuous but a seething foam at the Planck scale, where dimensions might fluctuate or even fractionate. Picture a pixelated image, zoom out and it looks like three-dimensional space. Zoom in, and the pixels reveal a chaotic, possibly multidimensional underpinning. The clash between these two giants, string theories, extra dimensions versus LQG's quantum spacetime, isn't just academic. It's a battle over how deeply we're willing to reshape reality. String theory demands we accept hidden dimensions as fundamental, while LQG suggests dimensions themselves might be emergent, like temperature arising from atomic motion. Both, however, hint at a deeper truth. The universe's geometry isn't fixed. It breathes, twists, and maybe even unravels under extreme conditions. Experiments could settle the score. If the Large Hadron Collider detects missing energy or micro black holes signatures of Kaluza-Klein gravitons, it would bolster string theory's multidimensional vision. Conversely, if gravitational wave observatories spot spacetime's granularity in the echoes of colliding black holes, LQG gains ground. There's even a wild card. Some models blend both ideas, suggesting extra dimensions could be quantum fluctuations frozen into place during the universe's cooling, like wrinkles in a crumpled sheet smoothed by time. What's exhilarating is how high the stakes are. Unifying gravity and quantum mechanics isn't just about tidying up equations, it's about decoding the universe's operating system. Whether through hidden dimensions or quantum space-time, the answer will redefine what we consider possible, rewriting not just physics textbooks but our very understanding of existence. And that's the real magic. The closer we get to a theory of everything, the more the universe reveals itself as a place where even the wildest ideas might just be the tip of a multidimensional iceberg. The hunt for hidden dimensions isn't confined to chalkboards and equations, it's playing out right now in labs and observatories around the world, where scientists are pushing the limits of technology to catch even a whisper of higher dimensional reality. Take tabletop gravity experiments, for instance. These aren't the colossal machines you might picture. Some fit on a desk, yet they're probing space down to scales 1 billion times smaller than a grain of sand. Devices like torsion balances and optomechanical cantilevers measure the gravitational tug between tiny gold spheres or vibrating membranes, searching for deviations from Newton's inverse square law. Why? Because if extra dimensions exist, gravity should strengthen dramatically at microscopic distances, like a hose suddenly unkinking to release a torrent. So far, no definitive crack in Newton's framework has appeared, but the precision is staggering. These experiments rule out large extra dimensions bigger than a micron, squeezing the possibilities into ever tighter spaces. Meanwhile, particle colliders like the Large Hadron Collider are staging their own dimensional showdowns. When protons collide at nearly the speed of light, the energy condenses into new particles, some of which might be Kaluza-Klein gravitons, hypothetical heavy echoes of gravity's higher dimensional vibrations. These particles would vanish into the bulk, leaving behind trails of missing energy in the detectors like ghosts slipping through walls. The LHC has scoured its data for these gaps, along with even wilder signatures like microscopic black holes that evaporate in a flash of Hawking radiation. While no black holes have materialized and no gravitons have gone rogue, each new energy level explored narrows the hiding places for extra dimensions. It's a cosmic game of hide and seek where every null result still tells us something profound. If dimensions are out there, they're either smaller or more warped than we've imagined. Astrophysics offers a third lens, turning the cosmos itself into a laboratory. When black holes merge or neutron stars collide, they send gravitational waves rippling through space-time, waves that might carry hidden imprints of extra dimensions. Some models predict that higher dimensional gravity could subtly alter these waves, damping their amplitude or adding extra harmonics, like an orchestra playing in a hall with unseen acoustics. Telescopes also scour the cosmic microwave background for anomalies patterns that could betray the influence of compact dimensions in the early universe's geometry. Even dark matter's gravitational grip on galaxies might hold clues. If it's ordinary matter trapped on a neighboring brane, its pull could reveal the shape of the hidden bulk. Yet for all this ingenuity, why is the evidence still so elusive? Part of the challenge lies in scale. If extra dimensions are compactified at the Planck length, a billionth of a trillionth the size of an atom, their effects might only manifest at energies far beyond our current reach. Warped dimensions add another wrinkle. Their influence could be localized in regions of space we've yet to probe, like a mountain range hidden just beyond the horizon. There's also the possibility that we're asking the wrong questions, that dimensions don't look like anything we've modeled, requiring entirely new mathematical languages to describe them. But the silence isn't discouraging, it's refining the search. Every experiment, every null result carves away another slice of possibility, guiding us toward the truth. Whether through a tabletop anomaly, a collider's missing energy, or a gravitational wave's whisper, the message is clear: the universe doesn't give up its secrets easily. And if we do find those hidden dimensions, it won't just be a triumph of science, it'll be a paradigm shift, revealing that reality's full picture has been hanging just out of frame all along. What if the universe isn't just described by math? What if it is math? That's the bold claim of Max Tegmark's mathematical universe hypothesis, a theory so radical it reshapes not just our understanding of dimensions but reality itself. Tegmark's idea is deceptively simple. Every mathematically possible structure doesn't just exist as an abstract concept, it exists physically, as a concrete universe in a vast, higher dimensional multiverse. Think of numbers on a page. We assume they're symbols pointing to something real, like 3 apples or 2 stars. But Tegmark flips this. The numbers are the reality, and what we call the universe is just one equation in an infinite textbook of cosmic solutions. This isn't just philosophy. The hypothesis slices through the fog of why our universe has the laws it does, why quantum mechanics, why general relativity. Because they're mathematically consistent, and in Tegmark's view, consistency equals existence. The implications for dimensions are staggering. Our familiar 4-dimensional spacetime might be one thread in a tapestry of universes with 5, 6, or even infinite dimensions, each governed by its own mathematical rules. Some could be static, frozen in timeless geometries. Others might pulse with alien physics where entropy runs backward or causality loops like a Möbius strip. But here's the twist: not all mathematical universes are created equal. Tegmark distinguishes between computable and uncomputable structures. Computable universes like ours run on equations that can, in theory, be simulated by an infinitely powerful computer. Their dimensions unfold predictably, their physics tractable to beings like us. Uncomputable universes, though, are wilder. Their dimensions might morph unpredictably, their laws changing faster than any observer could track. Imagine a cosmic kaleidoscope where gravity switches to anti-gravity at random, or where space has 7 dimensions on Mondays and 11 on Tuesdays. These aren't just hypothetical, they're mathematically valid, meaning they must exist somewhere in the multiverse's stack. Critics argue this stretches plausibility. If every math structure exists, why don't we see glitches, universes bleeding into ours? Tegmark's answer lies in dimensionality's insulation. Higher dimensional space could separate universes so completely that no interaction is possible, like parallel pages in a book that never touch. Others counter that Occam's razor favors simpler theories, but Tegmark retorts that his hypothesis is simple. It cuts the Gordian knot of why these laws. By declaring all possible laws exist, the real mind bender is how this reshapes consciousness. In a computable universe, beings like us can emerge to observe it, a self-selecting effect called the observership equation. Uncomputable realms might host alien intelligences or none at all, their dimensions too chaotic for stable life. It's a humbling thought that our perception of reality might be confined not just by 3 dimensions of space, but by the narrow slice of math that allows us to exist. Whether Tegmark's vision holds or not, it forces a profound question. Is math invented or discovered? If the latter, then hidden dimensions aren't just curiosities, they're inevitable, woven into the very fabric of existence by the cold, beautiful logic of numbers. And if that's true, then every equation scribbled in a notebook might be a window into another world, waiting in the shadows of dimensions we've yet to name. Hollywood loves a good extra dimension, whether it's bending time around a black hole in Interstellar or cracking open portals to the upside down in Stranger Things. But how much of this is cinematic flair, and how much brushes against real theoretical physics? Take Interstellar's portrayal of the 5th dimension, where Cooper floats behind his daughter's bookshelf, manipulating gravity like cosmic strings. The film consulted physicist Kip Thorne to ground its spectacle in science, and it shows. The idea that higher dimensions could warp spacetime isn't just plausible, it's central to brainworld theories. Where the movie takes creative liberties is in making those dimensions navigable. In reality, even if extra dimensions exist, they'd likely be curled up far smaller than an atom or locked behind insurmountable energy barriers, not a place you could punch through with a wristwatch. Stranger Things takes a darker, more metaphorical approach. The upside down isn't just another dimension, it's a shadowy twin of our world, echoing its structure but twisted by malevolent forces. This taps into a real, if speculative, idea in physics: mirror universes separated by higher dimensional space. Some theories suggest particles could have invisible counterparts in parallel branes, though the show's demogorgons are pure fiction. The one accuracy, the idea that crossing dimensions requires colossal energy. 11's psychic ruptures aren't far off from hypothetical brain collisions or quantum tunneling events, processes that would demand energies beyond anything we can produce. Then there's Doctor Strange, where dimensions are less realities than cosmic layers, folded like origami by sorcerers, visually dazzling, but the physics connection is thin. The movie treats dimensions like alternate planes with their own magic rules, closer to mysticism than M-theory. Yet it accidentally stumbles onto a real debate. Could consciousness interact with higher dimensions? Some fringe theories in quantum biology suggest microtubules in neurons might process quantum information in ways we don't yet understand, though no peer-reviewed study claims we can sling portals with our minds. Misconceptions abound. Most sci-fi conflates dimensions with parallel universes, but in physics, dimensions are directions, not destinations. A fourth spatial dimension isn't a hellscape or a utopia. It's just another axis, like length or width, even if we can't perceive it. Another Hollywood trope, portals as glowing doorways. In reality, traversing extra dimensions might not involve visible rifts at all. If higher dimensions are compactified, crossing them could look as mundane as particles vanishing in a detector. No sparks, no shimmering veils. What sci-fi gets right, though, is the weirdness. When Interstellar's characters experience time dilation near Gargantua, it mirrors how warped space-time in higher dimensions could distort clocks and rulers. Stranger Things' eerie synchronicity between worlds nods to quantum entanglement, where particles mirror each other across unimaginable distances. These touches matter. They prime audiences to think dimensionally, even if the details are dramatized. The takeaway: while Hollywood bends dimensions for plot, the truth might be stranger. A universe humming with hidden directions, unseen but essential, like the scaffolding behind a stage set. The real magic isn't in the special effects, but in the science slowly uncovering how much grander reality might be. Imagine a future where computers don't just process information in zeros and ones, but in geometric symphonies vibrating through extra dimensions. Hyperdimensional computing takes the idea of quantum bits, qubits, and flips it on its head. While qubits exist in superpositions of states, hyperdimensional systems could encode data in the very shape of compactified dimensions, using Calabi-Yau manifolds or other intricate geometries as their circuitry. Picture a processor where calculations aren't linear but unfold in higher dimensional rotations, solving problems in seconds that would take classical machines millennia. Drug discovery, climate modeling, even artificial intelligence could leap forward as these systems harness the exponential complexity of multidimensional math. The catch: we'd need to engineer materials that stabilize these structures, perhaps using topological insulators or exotic superconductors, but the payoff would redefine what's possible in computation. Then there's the dream of bulk space travel. If our universe is a three-dimensional brain floating in a higher dimensional bulk, crossing into that void could let us bypass the speed of light. Think of it like tunneling through a mountain instead of climbing over it, except the mountain is space-time itself. The Alcubierre warp drive, often dismissed as sci-fi, might find new life in extra-dimensional physics. By warping the bulk around our brain, a ship could effectively surf compressed space, never breaking relativity locally while crossing interstellar distances in weeks. The energy requirements are staggering, comparable to harnessing the output of a star. But if compact dimensions leak gravity in just the right ways, we might discover shortcuts hidden in plain sight. Energy extraction from compact dimensions sounds even wilder, but the math hints at tantalizing possibilities. If extra dimensions vibrate at specific frequencies, they could act like cosmic batteries, storing energy in geometries beyond our perception. Theoretical models suggest that Kaluza-Klein particles, those higher dimensional echoes of familiar matter, might decay into detectable energy bursts. Harvesting this would require technologies we can barely fathom, perhaps quantum nets that resonate with compactified dimensions, siphoning off microscopic tremors into usable power. It's a long shot, but so was nuclear fission once, the real game changer. These technologies wouldn't just revolutionize our tools, they'd redefine our place in the cosmos. A civilization harnessing extra dimensions wouldn't just explore the universe, it would dance with its hidden layers, uncovering truths about reality we've yet to dream. Whether any of this is achievable remains uncertain, but the theories are clear. The universe's greatest gifts might be tucked into dimensions we're only beginning to map. If we woke up tomorrow to definitive proof of hidden dimensions, it wouldn't just rewrite physics textbooks, it'd shatter the bedrock of how we perceive reality itself. The human mind evolved in a three-dimensional landscape, hardwired to interpret the world through length, width, and depth. Time, our fourth axis, already stretches intuition. Adding more would force a cognitive revolution. Think of the first humans grasping Earth's roundness, not as a flat plane under a dome, but a sphere hanging in void. extra dimensions demand an even more radical recalibration. Suddenly, concepts like here and there become provincial, like ants on a map unaware they're crawling across a globe. This isn't just about spatial axes. Confirmed extra dimensions would ripple into philosophy's deepest waters. Take free will. If higher dimensions host alternate versions of ourselves making different choices, does choice retain meaning? Or consider consciousness. Could our sense of self be a fragment of a broader, multidimensional mind? Even theology would grapple with echoes in ancient texts. Kabbalah Sephirot describes 10 emanations through which the infinite reveals itself. Hindu cosmology speaks of lokas, layered realities coexisting like pages in a book. Were these metaphors or glimpses of a truth now veiled by the limits of human perception? Then there's the nagging why 3 + 1 question. Of all possible dimensional configurations, why does our observable universe favor 3 spatial dimensions and 1 of time? Math offers clues. In 4 or more spatial dimensions, planetary orbits become unstable worlds, would spiral into stars or drift into darkness. Chemical bonds, too, depend crucially on 3 dimensions. Add more, and atoms might never form molecules. But this anthropic reasoning feels unsatisfying, like declaring the ocean exists solely to fill our cups. Alternatively, some theories suggest our 3 + 1 reality is just one slice of a richer structure. Imagine a cosmic kaleidoscope, tilt it slightly, and another dimensional combination dominates with its own physics, its own life forms pondering their universe's natural laws. The most haunting implication: we may forever be prisoners of our dimensional perception. A 2D being couldn't fathom depth, no matter how vividly you described it. Similarly, higher dimensions might hover at the edge of our intuition, their full nature forever beyond reach. Yet here's the beauty: science thrives at these edges. Every leap from Copernicus to quantum mechanics began by admitting how much we didn't see. Hidden dimensions, if real, wouldn't just expand the universe's map. They'd teach us humility, that reality's truest shape might always lie just beyond the limits of our gaze. The search for hidden dimensions has stretched our understanding of reality further than we ever thought possible. From the intricate folds of string theory's Calabi-Yau manifolds to the holographic whispers of information on a distant cosmic boundary, these ideas aren't just mathematical curiosities, they're glimpses into the universe's deepest blueprints. Brane world scenarios paint gravity as a force leaking into the cosmic bulk, while supersymmetry suggests every particle we know could have a shadowy twin vibrating through unseen dimensions. And then there's the holographic principle, turning our entire universe into a projection from a lower dimensional surface, a cosmic mirage more profound than any illusion. Yet for all their elegance, these theories remain tantalizingly out of reach. Why haven't we detected extra dimensions directly? Could it be that they're curled up smaller than we can probe, or warped in ways that hide them from our instruments? Or is the answer even stranger, that dimensions aren't fixed but fluctuate or even vanish at energies we've yet to harness? The silence of particle colliders hasn't killed these ideas, it's refined them, forcing physicists to dig deeper into the math and ask harder questions. The fact that we're still searching, still puzzling over gravity's weakness and quantum entanglement's spooky links, proves how alive the mystery remains. What's exhilarating is how much room there still is to explore. Future experiments, more sensitive gravity probes, next-generation colliders, even quantum computers might finally crack open dimensions we've only dreamed of. Or we might stumble onto something entirely unexpected, a twist in the story that rewrites the rules all over again. That's the beauty of science at the frontier. Every answer births new questions, and every discovery peels back another layer of the cosmic onion. So stay curious. The universe hasn't shown all its cards yet. Whether hidden dimensions turn out to be real or just a stepping stone to something even wilder, one thing's certain: reality is far richer, far weirder than our everyday senses suggest. The next time you look up at the night sky, remember, you might not just be staring into space, but into the folded edges of a reality we're only beginning to map. The adventure isn't over, it's just getting started.